These are the solutions to calculus homework number 25 from the textbook, as described right here at the top left of your screen. Number 3 says, in a time of t seconds, a particle moves a distance s meters from its starting point, where the function s is described as 3t squared. And A asks to find the average velocity between t equals 1 and t equals 1 plus h if you have certain values of h. So what I'm going to do is I'm going to start with, for A, s equals 3t squared. So what I want to do to find average velocity, if this is distance, so this is distance, my average velocity would be the following expression. So I could say this is v average rather than writing average velocity, and that would be S2 minus S1 over T2 minus T1. So what does this become? Well, if I'm looking at t equals 1 and t equals 1 plus h, that's going to be an S2 of of 1 plus h minus s of 1 over, well, my t is going to be 1 plus h, or my t2 rather, minus a 1, which is my initial time. So really my v average expression is going to be s of 1 plus h minus s of 1 over h, because I'd have 1 minus 1 on the bottom. So using this, I have several different values of h. So for part I, or 1, you have h equals 0.1. So I'm going to find my average velocity to be s of 1 plus 0.1, which is just 1.1, minus s of 1 all over 0.1. So if I go into my function, where s is 3t squared, that's going to be 3 times 1.1 squared minus 3 times just 1 squared, all over 0.1. So for this value of h, my average velocity will be 6.3, and that's going to be meters per second, because h is assuming in seconds here because we have t seconds. So that's part 1. Part 2, we're going to have h as a smaller value. So I'm going to have v average, in this case, will be s of 1 plus 0.01 minus s of 1 all over now my new h, which is 0.01. Again, you can look over here if you want to know where this is coming from. So my value here, I'm going to go to the right a little bit, is going to be 3 times 1.01 squared minus 3 times 1 squared all over 0.01. So my average velocity in this case is going to be 6.03 meters per second. And I think you might see a pattern at this point, but part I will be the same thing, just with an h value of 0.001. So I will have s of 1 plus 0.001 minus s of 1 all over 0.001. So that would be 3 times 1.001 squared minus 3 times 1 squared all over 0.001. So the average velocity here is going to be 6.003 meters per second. So there's my 3 average velocities with an increasingly small h. And B says, estimate the instantaneous velocity of the particle at time t equals 0. Well, if you look at these 3 velocities, as the time interval gets smaller and smaller, my average velocity seems to be getting closer and closer to a value of 6. So my instantaneous velocity, I might say, is very likely going to be 6 meters per second. And the reasoning here again is because V average is getting closer and closer to 6. as the interval gets smaller, or as h gets smaller. So question 4 says, find the average velocity over the interval from 0 to 0.8 and estimate the velocity of the car at position or at time 0.0 or 0.2. So here are my functions. So I want to find average velocity. So if you recall from the last problem we did, or question 3 previous, you will see that V average we had an expression for, and that was S2 minus S1 over T2 minus T1. So if I want to find the average velocity for this first interval, T1 would be 0, T2 would be 0.8. So I'm going to need to find S of T1, which is going to be 0, and S of T2, which is going to be 6.5. So my average velocity is going to be 6.5, and this is feet, minus 0, over 0.8, and this is in seconds, minus 0. So my average velocity will just be 6.5 divided by 0.8, which is, we're not going to round it all, 8.125 feet per second. And that's just for this time interval. Then it says, estimate the velocity at 0.2 given this table. So, what do we need to do in order to estimate the velocity at 0.2 seconds? So, the most reasonable way to do this is to kind of look at the velocity before and after. So I have two little sections. So I could look at it for 3 sections. So I could say for t from 0 to 0.2, what is my average velocity? Well, my average velocity is going to be, so it's going to be S2 minus S1, so that'll be 0.5, which is S at 0.2, minus 0, over 0.2 minus 0. So the average velocity for this is approximately 2.5, or it is 2.5 feet per second. And then if I look at the t from 0.2 to 0.4, how does this change? Well, the average velocity is going to be calculated as 1.8, which is S2, minus 0.5 over 0.4 minus 0.2. So my average velocity here will be 6.5 feet per second. So there's quite a big difference here. So to estimate the velocity at t equals 0.2, what I can do is I can just say it's going to be somewhere between 2.5 and 6.5. And so a good estimate might be between these two numbers. So between 2.5 feet per second and 6.5 feet per second. And that's the best I can do. So I could say maybe around 4 feet per second would be a good guess. For question 5, we're given another position function. This is s of t equals t squared. And we want to find the average velocity between t equals 3 and t equals 5. So real quick recap from previous questions. Our average velocity will be S2 minus S1 over T2 minus T1. So what I'm going to need to do for part A is I will need to find the average velocity by taking S of 5 minus S of 3 over 5 minus 3. And that's because T1 will be my first time, which is 3 seconds, and T2 will be my second time, which is 5 seconds. So my average velocity here is going to be 5 squared, because that's my function, or 5 substituted into my function, minus 3 squared over 5 minus 3. So the average velocity for this interval will be 8, and then the units say feet per second. Now B says, by using smaller intervals around 3, estimate the instantaneous velocity at t equals 3. So this is what I did in the first problem, number 3, in this homework. So what I'll do is I'll use smaller and smaller intervals. So I'm going to find an average velocity of, say, s of, let's do 3.01 minus s of 3 over 3, actually, so it's just going to be over my slight change, which in this case is 0.01. So in case you've forgotten, from number 3, we derived a situation where we had s of t plus h minus s of t over h. And h was just some little difference from t. And so in this case, I picked a very small h of 0.01. So I'm going to go through and I'm going to calculate these values. And so s of 3.1 is just going to be 3.01 squared minus 3 squared all over 0.01. So my average velocity for this little interval is going to be 6.01, and that's feet per second. Now I need to do at least 2 because I need to make sure that my number is getting closer to something. So I'm going to do this again. I'm going to use an even smaller interval. So I'm going to do s of 3.001 minus s of 3 all over my new h of 0.001. So that'll just be 3.001 squared minus 3 squared over 0.001. So my average velocity here is going to be 6.001 feet per second. Therefore, my instantaneous velocity at 3 seconds is very likely 6 feet per second, because these numbers are getting closer and closer to 6. For question number 6, we're given a graph of y equals f of x, and we have x on the horizontal and y on the vertical. Y represents a cost, x represents number of kilograms. And question A asks us to determine whether the rate of change of cost is greater between the 0 and 3x marks and x equals 3 and x equals 5. So if I look at the 0, my y value is right here. I'm going to change colors. If I look at the 0, my y value is right here. Maybe we'll do a darker color. And at the x equals 3, it is approximately right there. And the average rate of change is just the slope of the line that connects these 2 points. So my average rate of change will just be the slope of this line. Now, if I'm looking at the average rate of change between 3 and 5, that's going to be the slope of the line between these 2 points. So what I can say here, without a doubt, is that between the one on the left and the one on the right, one is steeper. Therefore, the average rate of change is higher, or you could say greater, because this slope is steeper. Now, B says, is the instantaneous rate of change of cost greater at x equals 1 or x equals 4? So I'm going to change colors again so that we can see this clearly. So I'm looking at x equals 1 versus x equals 4. So this is kind of the same deal. I'm looking at the slope, but I'm only looking at the slope at that one point, not the slope between 2 points. And so here, I will define the slope to be identical to the slope of the tangent line, if I were to sketch a tangent line at those 2 points. And if I were to do that, I would see something very similar to what we saw in A. The slope is much greater for the tangent line at x equals 1 than at x equals 2. So I can say the slope is steeper for x equals 1. Therefore, the instantaneous rate of change is higher or greater at x equals 1. Now C says, what are the units of these rates of change? So why not add one more color here? C says the units. So the units come from slope calculations. So my slope is just change in the vertical over the change in the horizontal. And the units for that would be thousands. Oops, that's not how you spell thousands. Thousands of dollars over kilograms. So I can say thousands of dollars per kilogram and leave it right there. Question 7 is looking at the size of a tumor given by the function s equals 2 raised to the t. And t is the number of months since the tumor was discovered. So A asks for the total change in size of the tumor during the first 6 months. So change in size is going to be delta S, which is defined as S2 minus S1. So that will be S of T2 minus S of T1. Well, S of T2 is going to be, in this case, 6 months, because 6 months have elapsed since discovering the tumor, and T1 will be 0. So my change in size is going to be 2 raised to the 6th minus 2 raised to the 0. So my change in size will be 63 cubic millimeters. In case you don't know how to write that, that would be mm, little m's, cubed. So this is my change in size for the first 6 months. Now B says, what is the average rate of change in size during those 6 months? Well, average rate of change is just S2 minus S1 over T2 minus T1. But we just calculated S2 minus S1 for the first 6 months. So all I need to do is say that T2 minus T1 is going to be 6 months, because I have 63 millimeters cubed over 6 months minus my time 1 of 0 months. So it's just actually 63 millimeters cubed divided by 6. So my average rate of change in the size of this tumor is just going to be 10.5. I guess I should include units, so this is months. So that'd be 10.5 millimeters cubed per month. C says, estimate the rate at which the tumor is growing at t equals 6. So here's where I want to use several small steps to calculate this. And so just in case we've forgotten, our instantaneous is going to come from S2 minus S1. I'm sorry, I should do it this way. S of t plus h minus S of t all over h. And again, this was derived in the number 3 that we did in this homework. So what we have here is going to be an average. So I'm just actually going to start abbreviating this as AROC. And that's going to be, we need to pick a small interval. So let's just pick 0.01. So we'll do 6.01 minus S of just 6 all over my h, which is 0.01, which is the difference between those two values. So this is going to be 2 raised to the 6.01 minus 2 raised to the 6th all over 0.01. So my average rate of change for this very small interval is going to be 44.5, we'll round it, and that's millimeters cubed per month. And then we'll do this again for an even smaller interval. So we'll say S of 6.001 minus S of 6 all over 0.001. And so this is just going to be 2 raised to the 6.001 minus 2 to the 6 over 0.001. And so my average rate of change for this very tiny interval is going to be 44.38, and that's millimeters cubed per month. So it's not very apparent what this is getting close to, so I'm going to do a third interval that's even smaller. So my average rate of change, one more time, we'll do S of 6.0001 minus S of 6 over 0.0001. And this average rate of change will just be 2 raised to the 6.001. I'm sorry, there should be another 0. 3 zeros. Minus 2 to the 6 over 0.0001. So this average rate of change will be 44.36. So I can make an estimate now that my instantaneous rate of change, so it is asking again for the rate at which the tumor is growing at 6 seconds. So my instantaneous rate of change is going to be approximately, let's say, 44.35 millimeters cubed per month. Because that is a good guess as to what this is getting closer and closer to. For question 14, we have a table of population data as a function of year. And so this steps every 30 years until the last 20 or so. So A asks us to find the average rate of change of percent of population living in urban areas between 1890 and 1990. So average rate of change, I'll just really abbreviate as AROC, is going to be the population percent in 1990, which will be 75.2%, minus my initial percent in 1890, which was 35.1%, over the years 1990 and 1890. So my average rate of change here is going to be 0.401% per year. Now question B says, estimate the rate at which this percent is increasing at the year in 1990. So, to do that, I'm going to find the average rate of change before and after the year 1990. So what we have here are two different average rates of change. So I have an average rate of change before, or going up to 1990. So that will be the 75.2 minus the 73.7 over 1990 minus 1980, or 10 years. And that average rate of change will be 0.15% per year. So this is my before, and my after the 1990 will be from 1990 to 2000, so that will be 79 minus 75.2 over 2000 minus 1990. And so that average rate of change is 0.38% per year. So between those two is going to be the actual rate, and so I might just average these to get an estimate for the actual rate. So 0.15 plus 0.38 over 2, or just the numerical average of this, is going to be 0.265. So I will estimate that the rate for 1990 is 0.265% per year. Now C says, estimate the rate of the change for this function in the year 1830. So for 1830, I have two intervals that I can do as well. So my first average rate of change is going to be from the year 1800 to 1830. So I'll do 1830 minus 1800, and then I will have 9 minus 6. So this average rate of change will just be 3 divided by 30, which is 0.1, and that's percent per year. And my other average rate of change is going to be on the other side of 1830. So that will be the 19.8 minus 9 over 1860 minus 1830. So this average rate of change will be 0.36% per year. So this, if I average them together, will be 0.1 plus 0.36 over 2, which is an average of 0.23% per year. Now D says, is this function increasing or decreasing? So keep in mind the phrasing here. Is the function increasing or decreasing? What is the function? The function is percent of population as a function of year. So if I look at this percent over time, it is increasing. So this function is increasing. A very common misconception, or not misconception, but easy point of confusion is thinking about how the rate is changing compared to how the actual function is changing. So be very careful when you're reading these problems. Question 15 asks you to plot two parabolas on the same set of axes. So I'll just do a quick sketch of what these will look like. So here are my x and y axes. My f of x I will plot in red, and that will be just a parabola. We can do that a little better. That goes through the origin and is symmetric about the origin. And then we have a second, which will be the same parabola, just shifted up by 3. So this right here is 3. Now, what can I say about the slopes of these lines at points x equals 0, 1, 2, and any other point? So if I look at the slope at 0, the tangent line is pretty much horizontal for both of these. In fact, it is horizontal. So the slopes are the same. In fact, if we look at tangent lines at any other point, the slopes are going to be identical in every single case. So the slope are always going to be identical, regardless of the fact that there is a vertical shift. Now B says, why does adding a constant to any function not change the value of the derivative? Well, if we add a constant to any function, think about how that affects our calculation for slope, or our average rate of change. We're going to have, in some cases, or in all cases, y2 minus y1 over x2 minus x1. And if our y, our function, involves some constant, so let's say our constant is c, we would have y, so we would have, actually just, let's look at it in this case, right? We're going to have x2 squared minus x1 squared over x2 minus x1. This is for f of x. If I change colors here, I could have x2 squared plus 3 minus x1 squared plus 3 over x2 minus x1, and this would be g of x. And what do you notice is going to happen? Well, I have plus 3 minus 3 over here. So these 3's end up canceling out. So any constant that we put in there will not end up affecting our slope, and therefore will not affect the value of the derivative at any point.